Welcome to this presentation about hydronic cooling systems. Hydronic refers to the fact that the needed cooling is transported through a water system, using the same kind of piping as for an hydronic heating system. Let's start with the cold conversion system. Those are chillers, also called cooling machines, which are in fact heat pumps in reverse mode or ATES systems, aquifer thermal energy storage systems, or systems using surface water like sea or river. No combustible are used, so it does not matter very much what is the location. In general, a central place on the roof or in the basement will be chosen. Sometimes there is also cooling district networks delivering cold obtained by an absorption heat pump elsewhere. The hydronic network will be identical to the network in heating mode, where here too a parallel design is recommended in such a way that the same temperature levels are guaranteed in all emitters. How does these emitters look like? Mostly, cooling panels in the ceiling are applied like on this figure, where chilled water circulates in small ducts at the upper side of the panels. Sometimes floor cooling is applied too, which looks like exactly as floor heating. When there are clear cooling and heating seasons, it is possible to use only one hydronic network for cooling and heating, but more often there will be two different piping systems to ensure some flexibility. The main problem with hydronic coolers is the occurrence of condensation if they are not well designed. If the room air is humid and the chilled water in the ducts is cold, it may be that the air comes below its dew point when flowing along the panel or the floor and then condenses. That's why these systems should always have a dew point temperature control, switching the cooling system off when approaching the dew point. So let's talk about dew point control and visualize it on the Mollier diagram. First, it is good to realize that in a hot and humid climate, hydronic cooling may not be the most efficient method because of the shape of the Mollier diagram. For instance, at 35 degrees and 50% humidity, the dew point is 23, while if the humidity is only 20%, we can cool down to 8 degrees without condensation. Maybe you ask yourself now, what is the point? Because why would we cool down to such low temperatures? Even 23 degrees in the first case is more than enough. Well, that has to do with heat exchangers and the needed temperature difference to achieve heat exchange. We need to keep the room air at 24 degrees. Therefore, TR, the water return temperature, must be below this temperature, let's say no more than 20 degrees. If the cooling load Q is high, the supply temperature TS needs to be low. You remember that Q is mCp delta T, so we may need a large delta T. Imagine that TS is 14 degrees Celsius. Air in a room is not still, it is moving all time. There is hot ventilation air coming in and being mixed with room air. There are airflows along the cooling panels. These airflows come in contact with the cold pipes in the panel and therefore cool down to 15 degrees, for example, before being mixed again with the room air. 15 degrees is below the dew point, therefore condensation will take place. In fact, one could say that the real process is not the purple one on the Mollier diagram, but the pink one. Some dehumidification takes place because of the cold water pipe. This is something that must be absolutely avoided, meaning that in such room heat exchangers, the water temperature should be kept above the dew point temperature any time. You see in the Mollier diagram for the left point with hot air at 20% humidity, that there will be no problems there, as the chilled water with its temperature of 14 degrees is far above the dew point of 8 degrees. Just like for the heating mode, we can size the emitter by using the law of conservation of energy and the log mean temperature difference. You may remember that in heating mode, the temperature difference between supply and return was around 20 degrees. In cooling mode, it is more limited because of dew point issues. In the example on previous slide, the temperature difference was only 6 degrees. If we take a new example where the room needs 7.5 kilowatt cooling, I remind you it is a large room of 125 square meter, we come to a needed surface area for the cooling panels of the cooling floor or the cooling floor of 154 square meter. You may remember from the lecture about hydronic heating that with the same load, the needed surface area was only 20 square meter. This is because much higher temperature differences are allowed in heating mode. This is also the reason that radiators like this one are not used in cooling mode. The surface area is much too small to produce enough cooling, and cooled ceilings or floors are preferred. Let's look further into these surface areas in hydronic cooling and take an example where we need 500 watt cooling to keep the room at 24 degrees Celsius. The formulas are identical to the formulas for hydronic heating. We assume a radiative heat transfer coefficient of 5 watt per square meter Kelvin and a convective one of 2.5. In general, cooling panels have no additional convective surface and are essentially radiant, so we'll consider AC is equal to A. The heat transfer equation can therefore be rewritten as this, and here too we can choose different combinations of size A and average temperature T emitter mean of the cooling panels. In the first example, the panel has a temperature of 10 degrees Celsius. It is an average temperature. In fact, as an example, chilled water may enter the panel at 8 degrees and leave it at 12. Never mind, with this temperature, a panel surface area of 4.8 square meter is needed. In the second example, the cooling panel has an average temperature of 14 degrees, with, for instance, a supply temperature of 12 and a return temperature of 16 degrees. This leads to a surface area of 6.7 square meter. And in the last example, the panel temperature is only 19 degrees, leading to a surface of more than 13 square meter. So, the higher the temperature of the cooling panel, the higher the needed surface area. The temperature levels given here correspond to what we call low temperature cooling, medium temperature, and high temperature cooling. Low hydronic temperature cooling is only possible in dry climates. That is why, in many climates, air cooling in an air handling unit is preferred. In an air handling unit, it does not matter very much if there is condensation. You can just drain it away. Summarizing, when chilled water with low temperatures below 10 degrees is used, the cooling panels may be small, and such a cold temperature can help with reducing the mean radiant temperature. However, from the energy point of view, the chiller will have low efficiency. Additionally, natural sources of cold, like shallow ground or surface water from rivers, lake, or sea, cannot easily be used, so that is not very satisfying. Such systems are easy to control. They react quick, so that is fine. However, a main risk is the one of condensation, by which dew point control must be applied, and the systems are not to be used in humid climates. Once again, such cold temperatures can better be applied in non-hydronic systems in air handling units, therefore. High temperature hydronic cooling with temperatures above 16 degrees has the advantage of being produced with a high efficiency, as the chiller needs to overcome only a small temperature difference between heat source and heat sink. Instead of chillers called from natural resources like night air, sea, rivers, or aquifer thermal storage systems can be used, which are very sustainable and produce almost no CO2 emissions. Concerning comfort, the building must be well insulated, otherwise the cooling panels will not compensate enough for too high surface temperatures of the walls, a too high MRT therefore. And even with high temperature cooling, a good dew point control is needed in case of humid weather. Last but not least, many buildings have a system with an intermediate temperature somewhere between 10 and 16 degrees, and depending on their design, they will share advantages and disadvantages of the high and low temperature systems. An alternative to floor or ceiling cooling at high temperature is activated concrete, sometimes used in larger buildings. Instead of having cooling panels below the concrete ceiling, water pipes are now placed inside the core of the concrete, and cold water is circulated at an average temperature of 21 degrees. The supply is at 20 and the return at 22, for instance, so a very high temperature chiller can be used. The concrete construction is therefore also at 21 degrees, which feels very comfortable. This system ensures a rather constant indoor climate and is able to deliver a basic cooling load. It is, however, very slow. A nice feature of activated concrete is that it can be used as a passive heating and cooling system in buildings that need simultaneously heating and cooling. This happens a lot, for instance, if a part of a building is oriented to the sun and needs cooling, while another part of the building needs heating, like on the picture. The rooms at one side of the corridor become too warm and need cooling, while the rooms at the other side are still too cold. It can happen in school buildings. The office rooms for teachers have low occupancy and needs to be heated a large part of the year in moderate climates, while the classrooms and meeting rooms need to be cooled because of their high occupancy. In such a case, the water in the pipes of the activated concrete is just heated by the hot rooms and cooled by the cold ones in a closed loop, without the use of any heating or cooling generation system. In this lecture, we studied hydronic cooling systems, which are room systems cooled by water. Just like for heating systems, the routing of the networks must be in parallel. Radiators are not used in general as their surface area is too small to produce the needed cooling capacity. The preference is to cooling ceilings and sometimes floor cooling. Much attention must be brought to the condensation problem, and dew point control is a must. You study the advantages and disadvantages of low temperature and high temperature cooling. High temperature cooling systems allow for higher efficiency chillers and the use of natural cold resources. Finally, we went into a specific application, which is activated concrete. Thank you very much for your attention. Goodbye.